About 400 million years ago, back when dinosaurs were already roaming the surface of a young Earth, two moons orbiting Saturn smashed into each other with enough violence to permanently rewrite the architecture of an entire planetary system. And it wasn't until earlier this year that scientists finally pieced together how that ancient catastrophe actually unfolded. For generations, the working assumption was simple. Saturn's rings had presumably been there from the very beginning, ancient leftover material dating all the way back to the formation of the solar system itself. Then, data beamed home by NASA's Cassini spacecraft quietly demolished that assumption. The rings, it turned out, are strikingly young, likely no more than a few 100 million years old, which means they didn't even exist yet when dinosaurs were already well established on Earth. That single discovery left planetary scientists with an enormous open question hanging over the entire Saturn system. If the rings weren't primordial material from the solar system's infancy, then where on Earth, or rather where around Saturn, did they actually come from? This past February, a newly published study finally offered what looks like a genuinely compelling answer, a cascading sequence of cosmic violence that played out, in astronomical terms, almost instantaneously. And sitting at the very center of that entire chain of events is Saturn's largest and most famous moon, Titan. Before getting into exactly how a single ancient collision manages to explain not just the rings themselves, but Saturn's oddly tilted axis and the bizarre, chaotic tumbling of one of its smaller moons, it helps to trace the story back to the very beginning of how humans first started making sense of Saturn at all. When Galileo Galilei pointed his primitive telescope towards Saturn in 1610, becoming the first person in recorded history to do so, he was thoroughly confused by what he saw. Saturn appeared to have two large companion bodies flanking it on either side, almost like a set of ears attached to the planet. 2 years later, those strange companions seemed to disappear entirely, only to re-emerge roughly 2 years after that, as odd protrusions Galileo described as handles jutting out from the planet's body. What Galileo was actually witnessing, without any way of knowing it at the time, was simply our shifting viewing angle on Saturn's ring system as the planet slowly journeyed around the Sun. Saturn's axis sits tilted at approximately 27 degrees relative to its orbital plane, which means the rings gradually tilt toward Earth and then tilt away again across Saturn's long orbital period. When those companion shapes seemed to vanish from Galileo's view entirely, he was simply catching the rings edge on, a razor-thin profile that his primitive optics simply couldn't resolve into anything recognizable. It took nearly half a century of continued telescope improvement before astronomers finally worked out what was actually going on. In 1655, Christian Huygens correctly determined that the strange handle-like shapes Galileo had documented were in fact a single continuous ring encircling the entire planet. Huygens also became the first person to spot Titan, Saturn's largest moon, during that same extended period of observation. As telescopes kept improving across the following decades, human understanding of the surprisingly intricate Saturnian system kept expanding right alongside them. Astronomer Giovanni Domenico Cassini went on to discover 4 additional major moons, Iapetus, Rhea, Tethys, and Dione, and in 1675 he became the first observer to spot a genuine gap running directly through Saturn's ring system, a distinctive feature that still bears his name today, the Cassini division. The next major leap forward arrived during the 19th century, driven in part by astronomer James Keeler, who demonstrated conclusively that the rings couldn't possibly be solid, continuous sheets of material as many researchers had long assumed. Instead, they had to be composed of countless individual particles, each one independently tracing its own orbit around Saturn. It wasn't until the late 1970s, though, that the true complexity and sheer beauty of the entire ring system finally came into sharp focus. Once NASA's Pioneer 11 spacecraft and later the twin Voyager probes flew past Saturn, each mission returning noticeably higher resolution imagery than the one before it. By the time Voyager 2 completed its flyby in August of 1981, it revealed for the very first time that Saturn's major rings were themselves composed of thousands upon thousands of individual, smaller ringlets, an almost unbelievably intricate internal structure hiding inside what had once appeared to be a handful of simple, uniform bands. Then came the Cassini mission, which spent well over a decade in orbit around Saturn, threading carefully through gaps between individual rings, skimming along their outer edges, and finally, in its dramatic closing chapter, repeatedly diving through the narrow gap separating the planet's cloud tops from its innermost ring, before ultimately plunging directly into Saturn's atmosphere to bring the mission to its planned conclusion. The sheer volume of data that spacecraft transmitted back to Earth completely reshaped our understanding of the Saturn system, filling in extraordinary detail while simultaneously uncovering a story genuinely nobody involved in the mission had anticipated going in. Saturn's rings, it turns out, are remarkably thin, somewhere between roughly 10 meters and 1 kilometer thick, depending on exactly where you measure, yet they stretch outward across a staggering distance of up to approximately 282,000 kilometers from the planet. They're named alphabetically in the order researchers actually discovered them rather than their physical position. So the major rings run D, C, B, A, F, G, and E, alongside one additional extremely faint outer ring called the Phoebe ring, sitting far beyond the others near the orbital path of the Moon, sharing that same name. Individual ring particles stay locked into their orbits partly thanks to a small collection of what astronomers call shepherd moons. Pan, Daphnis, and Prometheus sit directly within the ring structure itself, while Pandora, Janus, and Epimetheus orbit just beyond the outer edge of the F ring. Mimas, first spotted by William Herschel back in 1789, orbits considerably farther out, yet still exerts an outsized gravitational influence over the broader shape of the entire ring system, despite its relatively modest size. By the time the Cassini mission finally wrapped up, Saturn's confirmed moon count had climbed to 62. The discoveries certainly didn't stop there either, thanks to continued advances in ground-based telescope technology and more recent astronomical surveys. The current confirmed moon count now sits at nearly 300 and continues climbing, comfortably more than any other planet in our solar system. As a group, these moons turn out to be remarkably diverse, ranging from large, regular moons orbiting relatively close to Saturn within roughly the same orbital plane, out to a whole host of smaller, more distant, irregularly orbiting moons following steeply tilted and eccentric paths, all the way down to tiny, ravioli-shaped ring moons that gradually accumulate extra material around their equators, as fine dust drifting out of the rings slowly settles onto their surfaces over time. Cassini's detailed measurements also revealed precisely what the rings themselves are actually made of, and the answer is that they consist of roughly 99.8% water ice, with individual particle sizes ranging anywhere from smaller than a grain of sand up to chunks the size of a small mountain. It's the sheer reflectivity of all that bright, icy material that makes the rings appear so brilliantly luminous, even through comparatively modest telescopes here on Earth. Cassini's data also allowed researchers to calculate the total mass of the entire ring system, arriving at a figure of roughly 16 quadrillion tons. That number sounds genuinely enormous in isolation, but it actually works out to less than 0.02% of the mass of our own moon, a surprisingly tiny amount of material spread across such a visually spectacular structure. Putting those two particular observations together eventually led researchers toward a genuine scientific puzzle, and ultimately toward a major breakthrough. Over long stretches of time, micrometeorite impacts and drifting interplanetary dust gradually darken and pollute exposed water ice. So, if the rings had really been sitting in place since the earliest days of the solar system, why did they still appear so remarkably bright and comparatively clean? The relatively low total mass of the ring system actually allowed scientists to calculate roughly how much accumulated dust it would take to visibly darken material of that particular composition, and from there, roughly how long that gradual darkening process would realistically take. The surprisingly low ring mass strongly pointed toward the rings having formed somewhere between 10 and 100 million years ago, an almost impossibly brief window when measured against the solar system's full 4.6 billion year history, and dramatically different from what most researchers had assumed heading into the Cassini mission. Prior to this discovery, plenty of scientists genuinely believed the rings had simply always existed, forming right alongside Saturn itself billions of years earlier. Instead, it now appears dinosaurs had already been walking the Earth for something like 150 million years before Saturn's rings are currently thought to have even come into existence. So the obvious next question becomes exactly how the rings actually got there in the first place. This particular puzzle was first seriously tackled all the way back in 1848 by Edouard Roche, who was trying to understand why prominent ring systems tend to appear specifically around the largest giant planets. He proposed that tidal forces acting between a moon and its host planet, the very same underlying forces responsible for ocean tides here on Earth, could grow strong enough under the right circumstances to actually overwhelm the gravity holding a smaller moon together as a single coherent body. As Cassini's data continued piling up over the years, it became increasingly obvious that something genuinely catastrophic had happened somewhere within the Saturnian system, and relatively recently in cosmic terms, long after the planet itself had already formed. Back in 2022, a research team out of MIT proposed that Saturn's rings had formed following the destruction of an entirely separate, previously unknown moon that had once orbited somewhere between Iapetus and Titan, a hypothetical body the team nicknamed Chrysalis. According to their proposal, Chrysalis's orbit had been gradually disrupted by Titan's gravitational influence, eventually pushing it dangerously close to Saturn itself, where it was ultimately torn apart, its scattered debris spreading out to form the rings we still observe today. However, when that exact scenario was later modeled in far greater detail by a research team based at the SETI Institute, publishing their findings in February of this year in the Planetary Science Journal, it turned out to be considerably more likely that a doomed extra-moon like Chrysalis would have actually collided directly with Titan, rather than drifting close enough to Saturn to be shredded by the planet's own gravity. In that particular version of events, most of the resulting debris would simply have been absorbed by Titan's own powerful gravitational pull, or lost from the system entirely, flung outward into deep space, never forming anything resembling a proper ring structure at all. The research team, led by SETI Institute planetary scientist Mattia Chuk, along with collaborators from the Southwest Research Institute, Caltech, and the Observatoire de Paris, also noticed something else genuinely strange while running their Chrysalis-based simulations. Hyperion, a small, oddly shaped moon of Saturn's known for its chaotic, constant tumbling, kept getting completely ejected from the system entirely in the overwhelming majority of their simulated outcomes. But here's the obvious problem with that result. Hyperion very clearly still exists in the Saturn system today, and its orbit happens to be locked into a stable relationship directly with Titan's own orbit. The genuine breakthrough for Chuck's team came from recognizing that this particular Titan-Hyperion orbital relationship is actually quite young, dating back to roughly the same window of time when the hypothetical Chrysalis moon would have disappeared from the system for good. Hyperion, in other words, likely wasn't simply an improbable survivor of some earlier chaotic upheaval. It may have actually been a direct byproduct of that very same violent event. Chuck and his collaborators decided to widen their overall approach substantially, examining the entire Saturnian system as a single, deeply interconnected whole rather than analyzing each individual strange observation in isolation. That meant factoring in Saturn's unusual 27-degree axial tilt alongside detailed observations gathered from across its enormous family of moons. By treating the entire system as interlocking pieces of one larger puzzle, the team managed to simulate how these various events could plausibly have unfolded gradually across hundreds of millions of years. They ultimately concluded that Titan most likely did collide directly with an additional moon, one roughly 4 times more massive than the originally proposed Chrysalis, which they termed Proto-Hyperion, since the modern Hyperion we observe today would have needed to somehow emerge from that same violent collision. Titan itself would have looked noticeably different at the time as well, smaller than it appears today and following a much more circular orbital path around Saturn. Across their full set of simulation runs, a direct collision between Proto-Hyperion and Proto-Titan actually occurred in 42 out of 60 separate trials. In the remaining runs, where no collision took place, either Proto-Hyperion or Proto-Titan ended up getting ejected entirely from the Saturnian system instead. The team's best estimate places this dramatic collision at roughly 400 million years ago, setting into motion an entire chain of subsequent events that can now account for a surprising number of genuinely puzzling present-day observations scattered across the Saturn system. So what actually happened during this ancient catastrophe? The research team traced the underlying evidence back to a period when Saturn slipped entirely out of a stable spin orbit resonance it had previously maintained with the other giant planets in the solar system. Resonance, in this particular context, describes a situation where 2 orbiting bodies repeatedly settle into the exact same relative configuration over and over again, and small gravitational tugs, generated by each of those repeated encounters, gradually accumulate over time, amplifying their mutual influence on one another well beyond anything a single passing encounter alone could ever produce. In Saturn's specific case, that small underlying shift proved just enough to destabilize Proto-Hyperion's orbit, gradually pushing it into a tight 2-to-1 orbital resonance with Proto-Titan, considered one of the strongest possible resonance relationships 2 orbiting bodies can share. For every single orbit Proto-Titan completed around Saturn, Proto-Hyperion completed exactly 2. That relationship caused Proto-Hyperion to begin spiraling steadily inward, not only placing it directly on a collision course with Proto-Titan, but also gravitationally tugging on the orbit of nearby Iapetus along the way, pushing that particular moon onto the unusually tilted orbital path astronomers still observe it following today. Eventually, the orbital paths of these 2 proto-moons crossed directly, and the resulting collision unleashed genuine chaos throughout the surrounding system. The Titan we observe today is genuinely larger than the planet Mercury and stands as Saturn's single largest moon by a considerable margin. When the Cassini spacecraft eventually arrived at Saturn and safely delivered its accompanying Huygens probe down onto Titan's surface, the moon turned out to be wrapped in a thick, nitrogen-rich haze, with methane clouds actually raining down onto the surface below to form genuine flowing methane rivers and standing lakes. Titan's surface geology also turned out to look surprisingly young, showing remarkably few visible impact craters, strongly suggesting that its surface had been extensively resurfaced at some point relatively recently in its geological history. In Chuck's proposed scenario, when Proto-Titan catastrophically collided with Proto-Hyperion, enormous portions of Titan's surface would have been thoroughly resurfaced in the process, smoothing over older pre-existing impact craters and effectively giving the entire Moon a complete geological facelift. A large share of Proto-Hyperion's mass would have ultimately merged directly into Titan itself, while some of the remaining leftover fragments gradually reaccreted to form the small, misshapen Hyperion we still observe orbiting Saturn today. The outcomes produced by these simulations line up remarkably well with actual real-world observations. Most strikingly, the fact that Hyperion appears to be only somewhere around 400 to 500 million years old. Its irregular, lumpy shape and notably low density both align neatly with a body that formed out of loosely bound leftover debris rather than gradual accretion from the earliest days of the solar system. And its genuinely chaotic, tumbling rotation pattern remains fully consistent with raw momentum carried over from that original violent collision. Not particularly long after its formation, Hyperion was gravitationally captured by nearby Titan, and the two moons remain locked today in a stable orbital resonance relationship. As for Titan itself, the sheer force of that ancient collision pushed it onto a considerably more elongated elliptical orbital path, a gradual process that had actually already begun once Titan first became resonant with Proto-Hyperion, then accelerated dramatically once the actual collision occurred. Much like our own moon slowly drifting away from Earth today, ongoing tidal interactions are steadily pushing Titan farther away from Saturn as well. But there's an additional twist buried in this part of the story. Cassini's precise tracking data revealed that this particular outward drift is happening considerably faster than earlier models had ever predicted, at a rate of roughly 11 centimeters every year. A genuinely massive collision like the one modeled by Chuck and his team can neatly account for that unexpectedly rapid rate of orbital drift, something earlier, more conventional models had consistently struggled to explain. And the ripple effects from this newly enlarged, faster drifting Titan reach even further than that. As Titan's orbit changed shape and gradually expanded outward, it swept gravitationally through the wider Saturnian system, generating genuine dynamical chaos and eventually affecting Saturn itself. As we've already seen throughout this story, orbital resonances play an enormously important role across the solar system. And they don't only occur when two separate orbits happen to align with each other directly. They can also link the orbital motion of one body directly to the spin behavior of an entirely different one. Planets are never perfectly round spheres. The combined gravitational influence of the Sun and their surrounding moons flattens them slightly into what scientists call oblate spheroids. That same underlying effect also causes planets to gradually wobble as they spin along their axis, much like a child's spinning top slowly wobbling as it loses momentum, a phenomenon astronomers refer to as precession. Following that ancient collision, Titan's rapidly expanding orbit altered Saturn's own precession pattern, causing the entire planet to wobble on its axis progressively faster over time. That accelerating wobble eventually pushed Saturn's axial spin directly into resonance with Neptune's own orbital motion around the Sun. The only way that particular resonant lock could actually be sustained as Titan kept drifting steadily farther away was for Saturn itself to gradually tilt over onto its side. Given how giant planets typically form, they're generally expected to end up with close to zero axial tilt, which is precisely why Saturn's pronounced 27-degree tilt puzzled astronomers for such a long stretch of time. The scenario modeled by this SETI-led research team stands as one of the more genuinely convincing explanations proposed so far for that long-standing anomaly. For roughly the next 200 million years or so, the broader Saturnian system settled back into relative stability. But as Titan's steady outward drift kept quietly continuing in the background, it wasn't particularly long, in cosmic terms, before it triggered yet another round of disruption. About 100 million years ago, Titan's expanding orbit became newly locked into a resonance relationship with a pair of smaller inner moons, proto-versions of what would eventually become Dione and Rhea. That new relationship gradually tilted those inner moons' orbits and shifted their orbital paths, eventually driving the pair directly into collision with one another. The combined force of that impact, along with Saturn's own powerful tidal influence, tore those two inner moons apart entirely, producing an enormous quantity of scattered debris. Over time, some of that leftover material gradually reaccreted into brand new small moons. Some was lost from the system permanently, and the remainder spread out into the thin, flattened orbiting disk of material we now recognize as Saturn's iconic rings. That, according to this new model, is essentially how the rings ultimately came to exist, and it's also exactly why they turned out to be so surprisingly young when Cassini finally measured them directly. Now that the story has effectively come full circle, it's worth stepping back to take stock of everything it actually manages to explain. The oddly tilted orbit of Iapetus, the unusual age and lumpy shape of Hyperion, Titan's unexpectedly thick atmosphere, Its surprisingly youthful surface and its steadily expanding elliptical orbit, Saturn's own dramatic axial tilt and its accelerating wobble, and of course those stunning iconic rings themselves, all turn out to be different pieces of one single, genuinely violent underlying story. And all of it traces back directly to Titan. This particular model represents the first serious attempt to tie together so many previously unexplained observations of the Saturn system into a single, coherent scenario. It's a genuinely bold hypothesis. The obvious next question is whether it can actually be confirmed through future direct observation. Fortunately, a brand new mission to the Saturn system is already well underway in development. NASA's Dragonfly mission plans to send a nuclear-powered, roughly car-sized rotorcraft directly to Titan's surface. It will be capable of flying between multiple different landing sites across the Moon, collecting and carefully analyzing surface samples from several separate locations. Equipped with an extensive suite of onboard scientific instruments designed to study Titan's surface composition and atmospheric chemistry in fine detail, the mission carries genuine potential to uncover direct physical evidence supporting this proposed history of large-scale ancient resurfacing. Currently scheduled to launch in 2028, Dragonfly is expected to actually reach Titan sometime in 2034. Chuck and his fellow researchers close out their published paper with a direct nod toward this upcoming mission, noting that even if the precise sequence of events they've proposed never gets fully confirmed by direct observation, they still believe their broader framework can help shape entirely new hypotheses about how Saturn's remarkably complex system of moons has continued evolving over time. There's something genuinely important buried in that closing note about how science actually tends to work in practice. None of the underlying physics involved in this remarkable study is actually new. Orbital resonance, precession, and tidal forces are all extremely well understood concepts individually, each studied extensively on their own for decades. What this particular research team managed to do instead was demonstrate just how elegantly interconnected all of these familiar, individually unremarkable processes can actually become once applied together in sequence across an entire planetary system. As for the rings themselves, Cassini's dramatic final act, repeatedly diving through the narrow gap separating Saturn's cloud tops from its innermost ring, before eventually plunging directly into the planet to end the mission for good, revealed that Saturn's rings remain in a constant state of change even today. Individual particles are perpetually jostling against one another, and a significant amount of material continuously falls into Saturn's atmosphere as a steady rain of fine ice particles amounting to as much as 40 tons of material every single second. That ongoing, continuous loss of material strongly suggests the rings themselves may only persist for another few hundred million years, before eventually disappearing entirely. The wider Saturnian system has earned itself the nickname a dynamicist's paradise among researchers, and its deeply interconnected evolution genuinely continues unfolding even today, in real time, as material keeps raining steadily into Saturn's atmosphere and the rings keep thinning further with each passing century. It raises a genuinely fascinating question worth sitting with for a moment. What might this entire system actually look like another 100 million years from now, once still more material has rained down into Saturn's clouds and the rings have thinned even further than they already have today? As it turns out, we happen to be remarkably fortunate to exist at precisely the right sliver of cosmic history to witness Saturn's spectacular rings at all, a fleeting, temporary feature of the solar system that the dinosaurs never actually got the chance to see, and that future generations many millions of years from now may never get the opportunity to witness either. It's a strange thought to sit with, that something as vast and seemingly permanent as Saturn's rings is really just a brief cosmic event unfolding on a timescale we happen to be alive for, bookended on one side by a violent ancient collision, and, on the other, by a slow, steady rain of ice quietly falling into Saturn's clouds. What makes this entire chain of reasoning so satisfying, from a purely scientific standpoint, is how many previously disconnected mysteries suddenly resolve themselves once a single unifying event gets placed at the center of the story. Before this study, researchers studying Saturn's rings, its axial tilt, and its strange collection of moons were often forced to propose separate, unrelated explanations for each individual puzzle. One theory to explain the rings, another entirely different theory to explain Saturn's tilt, yet another to account for Hyperion's bizarre tumbling behavior. Science tends to move forward in exactly this kind of way, accumulating isolated explanations for isolated problems, until eventually someone recognizes that several of those supposedly separate puzzles might actually share a single common root cause. That's precisely the shift Chuck and his colleagues managed to pull off here, replacing a scattered collection of loosely connected coincidences with one continuous, physically consistent narrative stretching across hundreds of millions of years. It's also worth remembering just how recently in the broader arc of scientific history all of this became possible at all. Galileo squinted at Saturn through a telescope barely capable of resolving its rings as anything more than strange, ambiguous shapes. Just over 4 centuries later, humanity had built a spacecraft capable of orbiting Saturn for more than a decade, threading needle-thin gaps between individual rings, and ultimately gathering enough precise data to reconstruct a 400-million-year-old planetary collision down to the level of individual orbital resonances. That's an almost dizzying leap in observational capability, and it's exactly the kind of leap that made a study like this one possible in the first place. Without Cassini's extraordinarily precise measurements of ring mass, ring composition, and Titan's exact rate of orbital drift, none of the underlying evidence supporting this new collision model would have existed for researchers to work with at all. There's also something worth noting about how this story connects to the much longer arc of planetary science generally. Every major planet and moon in the solar system carries some version of its own violent formation history written into its present-day characteristics, whether that's the enormous impact basin scarring Mercury's surface, the moon-forming collision widely believed to have struck early Earth, or the tilted axis of Uranus, thought to be the result of an ancient impact entirely its own. Saturn's story, according to this latest research, fits neatly into that same broader pattern, a reminder that the calm, orderly appearance of a mature solar system today often conceals an extraordinarily violent and chaotic history playing out over the preceding billions of years. Rings, moons, tilted axes, and elongated orbits all frequently turn out to be fossilized evidence of ancient collisions, still quietly readable by anyone with the right instruments and the patience to look closely enough. For now, the picture remains a compelling hypothesis rather than settled fact, awaiting further confirmation from missions like Dragonfly, still years away from actually reaching Titan's surface. But even as an unconfirmed model, it already represents a genuine shift in how scientists think about the Saturn system as a whole, no longer as a collection of separate, individually curious oddities, but as the visible aftermath of one continuous, interconnected story of collision, resonance, and gradual transformation, still actively unfolding today, one ring particle at a time, raining quietly down into Saturn's clouds.